Hi viewers, in this video we will solve problem 1.7 from book Heat Transfer J.P. Holman 10th editions. Here is the statements. A 50 centimeter diameter pipeline in the Arctic carries hot oil at 30 centigrade and is exposed to surrounding temperatures of minus 20 centigrade. A special powder insulation of 5 centimeter thick surrounds the pipe and has thermal conductivity of 7 milliwatt per meter centigrade. The convection heat transfer coefficient on the outside of the pipe is 9 watt per meter square centigrade. Estimate the energy loss from the pipe per meter length. Okay, so the data that is provided, so the diameters of the pipe, the inside diameters of the pipe is 50 centimeter. You can say just divide 50 centimeter with 100, so it will convert into meter, that is 0.5 meter. Okay, so the Ri will be equal to di divided by 2 and it will become 0.25 meter. Next it says the oil that is inside this pipe is at a temperature of Ti, inside temperature that is 300 centigrade, and the outside temperatures here, so the outside temperatures is T infinity, let's say, and the inside temperature is Ti, and this is the inside diameters and that is Di. Okay, so the outside temperature that is at a cool region, so that is minus 20 centigrade. So it is obvious that heat transfer is taken place from this hot oil to the surrounding. Then we need to find how much heat loss per length on this pipe is occurs. Okay, so the pipe and has thermal conductivity of, what is the thermal conductivity of pipe? That is 7 milliwatt per meter centigrade. The convection heat transfer coefficient on the outside of the pipe is, so what is the convection heat transfer coefficient? That is 9 watt per meter square. So we need to find the heat loss per unit length of this pipe. And there is also the thickness, a special powder insulation of 5 centimeter thick surround. So this is the thickness of the insulations that is provided, and that is X, and that is equal to 5 divided by 100. So I am converting it into meter, that's why I divide the 5 centimeter by 100, so it will be equal to 0.05 meter. So if I find the outer dia D naught will be equal to, so the what is mean outer dia? Outer dia means the dia that is touching the extreme sides of the pipe, that's called outer dia, and it will be equal to inner dia plus 2 times of the thickness of the insulation that is provided. So that is equal to Di, the inner dia is 0.5 plus 2 into X, that is 0.05. So upon simplifications you will get that is 0.6 meter. So what will be the R naught? That will be equal to D naught divided by 2, and you will get that is 0.3 meters. So the R naught value will be 0.3 meters. I hope you understand this concept, why I add 2 times of the thickness of insulations. Okay, next, if you consider here the heat transfer that is taken place, first conduction is occur inside the pipe. So if I draw the resistance diagram, so first conduction resistance occur or conduction resistance occur in the pipe. Then next is the convection. This is the convection heat transfer occur. So the convection resistance is occur to the heat transfer. We need to find that. So convection, this is convection resistance occur to the heat transfer outside of the pipe, and inside the pipe there is a conduction heat transfer occurs, and there will be must be a conduction resistance occur. So the inside temperature is Ti and the outside temperature is T. So the R conduction, so the resistance to the conduction heat transfer, that is will be equal to ln R naught divided by Ri divided by 2 pi KL, and resistance in convection heat transfer, that is occur, that is 1 divided by HA. So what is H? HA is the convection heat transfer that is given in the statement, and A is the surface area of this pipe. So the surface area of the pipe is equal to pi d naught into L. So here I can write that pi d naught L. Now I want from the Fourier's law, heat transfer is equal to change in temperatures, that is Ti minus T infinity divided by the resistance that is offered to the heat transfer, that is conduction plus convection. Okay, so Ti minus T infinity divided by what is our conduction, that is ln R naught divided by Ri divided by 2 pi KL plus what is our convection, that is 1 divided by H pi d naught L. Now I want to find the heat transfer per unit length of the pipe. So I will divide both sides with L. So this L will be cancelled out with this L, and you will get heat transfer per unit length. The final expression is Ti minus T infinity divided by ln R naught divided by Ri divided by 2 pi K plus 1 divided by H pi d naught. Now each value on this side has been calculated. Now we just put these values in this formulas, and you will get the heat transfer per unit length of the pipe. So let me put the value. A heat transfer per unit length, that is equal to Ti, that is given, that is 30 centigrade plus, and what is the temperature, that is minus 20, so minus become plus, and it will be 20 divided by ln. So what is R naught, that is 30, or you can take 0.3 divided by 0.25 divided by 2 pi multiplied with K. What is K? That is of the pipe, that is 7 milliwatt per meter centigrade. So I can say that's 7 multiplied by 10 to the power minus 3 plus 1 divided by what is H, that is 9, that is given, pi, what is d naught, that is 0.6. So after simplification this on the calculator, you will get its value, that is heat transfer per unit length. So the heat loss, you can say, that is occur from the pipe per unit length will be 11.89 watt per meter. I hope you understand. If you still have any confusion, you can ask in the comment sections. Thank you so much. Please subscribe my channels for more such videos.